In this video, we're going to talk about the solutions to the final exam on probability and statistics spring 2017. We are going to go through the solutions to the 7 problems on the following topics. So let's start with the first one. It is about the conditional probability. So let's go through the problem and write the notation. A test has been developed to detect a particular disease for the individuals over 60 years. So from a survey, it is known that approximately 15% of the people in this group have the disease. Probability that a person has a disease is equal to the 0.15. So we are going to propose a test, and this test is positive in 80% of the cases if a person has a disease. So basically, probability that the test is positive if a person has a disease is 0.8, and in 4% of the cases, the test is positive for the persons who doesn't have this disease. So probability that test is positive if a person is free of this disease is equal to the 0.04. So we need to find the probability that a person has a disease if the test is positive, right? So if the test is positive, what is the probability that a person has a disease? So in order to solve this problem, we're going to use the Bayes theorem. So this is going to be equal to the probability that positive test for the person who has a disease multiplied to the probability that a person has a disease divided to the probability of we are going to get a positive test answer, right? So this is given, so this is equal to 0.8, and also probability that the person has a disease is also given 0.15. We need to evaluate the probability that the test is going to give us the positive answer, and in order to evaluate this, we're going to use the law of total probability. So this is going to be, we are going to have the positive test, either a person has a disease multiplied to the probability the person has a disease, or in a case when the person doesn't have the disease, multiplied to the probability the person doesn't have the disease. So probability that this case, the test is positive if a person has a disease is 0.8, multiplied probability a person has a disease is 0.15, plus probability the person have the positive test answer if he doesn't have the disease, this is going to be 0.04, and probability the person doesn't have the disease is equal to the 1 minus probability that person has a disease, which is going to be equal to 0.85. Right? So we're going to substitute everything here in order to evaluate this. This is going to be equal to the 0.8 multiplied to the 0.15 divided to the 0.8 multiplied to the 0.15 plus 0.04 multiplied to the 0.85. If we evaluate this, this is going to be 0.779. Problem number 2 is on the Poisson distribution. Earthquakes in Sumatra occurs according to the Poisson distribution with the minimum rate, right? Mu in 1 year is 2 earthquakes per year. So in average, 2 earthquakes happen in Sumatra in 1 year. So condition it on the events that exactly 2 earthquakes take place in 1 year. What is the probability that both earthquakes happen in the first 3 months of this year? So basically, we need to find the probability that 2 earthquakes happened. What is the probability that 2 earthquakes will happen in the first 3 months, which is equal to the first quarter of the year, right? Given that 2 earthquakes happens in this year. So in order to evaluate this probability, we're going to again use the Bayes theorem in the slightly different form. So this is going to be equal to the probability that 2 earthquakes are going to happen in the first quarter and 2 earthquakes happen in 1 year divided to the probability that 2 earthquakes happen in 1 year. So this is going to be equal to probability that, so this is probability that 2 earthquakes happen in the first quarter and 2 earthquakes happen in the same year. So this is equal to evaluating the probability that 2 earthquakes happened in the first quarter multiplied as the probability that no earthquakes happen in the rest of the year. So from 1/4 until 1, right? So divided to probability of T earthquakes happen in the same year. So in order to evaluate this probability, let us evaluate each of the probabilities using the formula for the Poisson distribution. Probability that X event will happen in the interval of time, this is going to be equal to the e in the power of minus lambda multiplied to the lambda in the power of x divided to the x factorials, where lambda is the average number of the events happening in that interval, right? So probability that T events happens in the interval between 0 and 1/4 is going to be equal to the e in the power of minus lambda. So lambda here is the average number of the events earthquake happening in 1/4. This is equal to the T multiplied to the 1/4, right? So if T earthquakes happen in 1 year in average, then half the earthquake happen in 1/4 of the year. So this is going to be equal to minus T multiplied to the 1/4. So T multiplied to the 1/4 in the power of T divided to the T factorials. So probability that 0 earthquakes will happen in the interval between 1/4 and 1, this is going to be equal to the e in the power of minus 3 T multiplied to the 3/4. So T multiplied to the 3/4 in the power of 0 divided to the 0 factorials. And probability that T events, T earthquakes will happen in 1 year is equal to the e in the power of minus T in the power of T divided to the T factorials. So we just need to put everything to the formula. So probability that T earthquakes will happen in the first quarter, given that T earthquakes happen in 1 year, is equal to e in the power of minus T multiplied to the 1/4 multiplied to the 1/8, e in the power of minus T multiplied to the 3/4 divided to e in the power of minus T in the power multiplied to the T. So if we cancel everything out, so we're going to have the answer 1/16. So let's go to the problem number 3. It's about the probability mass function of the discrete random variables. So in the first part, we just need to calculate the expected value of this random variable t. So we calculate the expected value of a random variables in the discrete case by summing up the outputs to their probabilities, right? So ti multiplied to the p of ti. So this is going to be equal to 1 multiplied to the 0.15 plus t multiplied to the 0.18 plus 3 multiplied to the 0.28 plus 4 multiplied to the 0.22 plus 5 multiplied to the 0.18, and this is going to be equal to 3.1. So in order to evaluate the variance, we're going to use the formula. So the variance of the t is equal to the expected value of the t square minus the expected value of the t in the square. So in order to evaluate the expected value of the t square, we are going to use the formula of the expectation of a function of the random variable. This is going to be equal to the ti in the square multiplied to the appearance of the ti. So this is equal to the 1 multiplied to the 0.15 plus 4 multiplied to the 0.18 plus 9 multiplied to the 0.27 plus 6 multiplied to the 0.22 plus 25 multiplied to the 0.18. And if we evaluate everything, we're going to get the answer 11.32. So in order to calculate the variance, then we need to put everything here to the formulas. This is going to be equal to the variance of the t is equal to, so 11.32 minus 3.1 in the square. So this is going to be equal to the 1.71. So in the second part of this problem, we need to calculate the probability that t is bigger than 3, given that t is bigger than t. So probability that t is bigger than 3 if it is given that it is bigger than 2. So we're going to evaluate this using the Bayes theorem again. So probability that t is bigger than this 3 and t is bigger than t divided to the probability that t is bigger than t. Right? So what is the intersection of the event? So t is bigger than this 3 and t is bigger than t. Right? So the intersection is going to be equal. So bigger than 3 and bigger than t. So intersection is going to be all the events are like when the t is bigger than 3. Right? So we need to, in order to find a probability that t is bigger than 3, we're just going to add those probabilities. So this is going to be equal to the probability that t is bigger than 3 and t is bigger than t. So in order to evaluate the probability that t is bigger than t, we just need to sum those values. So this is going to be equal to the probability that t is bigger than t. So we just need to put all the numbers and sum them, and we're going to get the answer 67 over 85. So in the last part of this problem, we need to evaluate the expected value of the t given the t is more than t. So what is the average value for the t if it is already given that t is bigger than t? So in order to do this, we're going to evaluate this using the formula for the expected conditional expectation. So the expected value of the t, if the t is given more than t, is equal to the summation of the ti multiplied to the probability of ti given that t is bigger than t, and we just need to sum this. So this is going to be equal to, so I'm going to extract this formula using the Bayes theorem. So this is going to be equal to the summation of t multiplied to the probability of the t and t is bigger than t divided to the probability of t is bigger than t. So the intersection of the any t value and t is bigger than t is going to be t is bigger than t, and I'm going to evaluate this by multiplying t multiplied to the 0.18 plus 3 multiplied to the 0.27 plus 4 multiplied to the 0.22 plus 5 multiplied to the 0.18 divided to the probability of t is bigger than t. It is just the summation of all the probabilities when t is more than t. This is going to be equal to the 0.18 plus 0.27 plus 0.22 plus 0.18. If we evaluate this, we're going to get an answer 277 divided to the 85. Let's go to the problem number 4. It's on the on the continuous probabilities. So we're given a density function. We need to find a value for the c so that this function becomes a proper density function. So we know that a function is called a density function if we integrate this in a whole range of the random variable from 0 to the t in this case, right? Otherwise it is equal to the 0, is equal to the 1. So we just need to integrate this and equalize this. This is 1 in order to find a value for the c. So this is going to be equal. So 2c minus cy, its integration from 0 to the 2, is equal to the 2cy minus cy squared over t, because we're integrating with respect to the y, and we need to put the values from 0 to the 1. If we put them, we're going to, so let's put the 1 to the instead of y. So it's going to be 2c minus c over t, right? 2c minus c over t. And if we put the 0, it's going to be 0 and 0. So I need to equalize this to the 1. So this is going to be equal to the 4c minus c is equal to the 2. So 3c is equal to the 2, so that is why c is going to be equal to the 2 over 3. Right? Okay, so in the second problem, we need to find a cumulative distribution function, right? So find a cumulative distribution function f of y. So according to the definition, this is the probability that big random variable is less or smaller than small one. This is equal to the integration from minus infinity, or in our case from 0 until the y of the density function. I'm just going to denote this different with a different letter. So let me write as f of t. Okay, so in this case it's going to be f of t dt. So I just need to substitute the f of t here. It's going to be integration from 0 to the y. So t over 3 multiplied to the t minus y, t over 3 multiplied to the t minus t dt. So we just need to integrate and evaluate the integration, the definite integration. This is going to be equal to t over 3 2t minus t squared over t from 0 to the y. If I substitute the y, it's going to be t over 3 ty minus y squared over t. So this is the formula for the cumulative distribution function of this distribution, of this random variable. So in the problem number 3, we need to evaluate the probability that y is less than 1, given that the y is less or equal to the 1 over 5. So probability that y is less than 1, given y is less or equal to the 1 over 5, is going to be equal to the probability that y is less than 1 and y is less or equal to the 1 over 5 divided to the probability that y is less or equal to the 1 over 5. So please note that in the continuous case, it doesn't matter where you find the probability less or less or equal. In both of the cases, we are going to do the integration. So probability that y is less than 1 and y is less or equal to the 1.5, it's going to be, we are going to find the intersection of the intervals, right? 1 over 1.5. So what is the intersection of y is less than 1 and y is less or equal to the 1.5? The intersection is going to be this range when y is less than 1. So probability that y is less than 1 is the integration of the density function, right? Or we just need to evaluate this as the cumulative distribution function at the 1. So probability that y is less than 1. And divided to the cumulative distribution at the 1.5, it's a probability that y is less than 1.5. So we just need to evaluate the values using this function. So this is going to be equal to the t over 3, so t minus 1 over t, divided to t over 3, t multiplied to the 3 over t, minus 9 over 8. So by simplification, we can evaluate this. So t over 3 and t over 3 are going to be cancelled. T minus 1 over t is going to be equal to the 3 over t. And here's 3 minus 9 over 8. It's going to be equal to 3 minus 24, 15 over 8. So we can cancel this and this. It's going to be 5 here. Cancel this and this. It's going to be 4. It's going to be 4 over 5 or 0.8. Okay. So, and the last problem is about the conditional expectation, right? So we need to find the conditional expectation of the y if the y is less than 1.5. Conditional expectation of the y if the y is less or equal than 1.5 is found, again, using the formulas. It's going to be equal to integration of the y multiplied to the 3 over t, t minus y from 0 to the 1.5 divided to the integration of simply 3 over t, t minus y from 0 to the 1.5. So it's like basically in order to evaluate this expectation, I just need to evaluate the expectation, conditional expectation here, right? You see, so I'm multiplying the y to the density function divided to the probability that y is less than 0.5. So after evaluating, we can find the answer 0.6. So it's like a straightforward integration. So problem number 5, it's about the exponential distribution. So a life of a certain electronic component x, the lifetime, obey an exponential model was the mean life of 11 hours, right? It's like x has the exponential distribution, with the mean theta is 11 hours. So basically it's about the lifetime, or it's about the exponential distribution may be used for the models of the lifetime or models of the waiting time between the t events and so on. So in the first problem, find the half-life of such a component. So basically we need to find the probability that x is more than b, so that this is equal to the 1 over t. Okay, so this is the probability that x is more than b is equal to the probability that x is less or equal to the b and 1 minus of this, right? So we are going to use the formula for the exponential distribution. The formula of the exponential distribution was equal to e in the power of so probability that x is less than the density function of the exponential distribution is equal to the lambda, or e in the power of minus lambda x, or we can write this with the theta. It's going to be 1 over theta e in the power of minus x over theta. And also it is worth to note that the cumulative distribution function for the exponential distribution, it's the probability that x, the random variable smaller than this x, is going to be equal to the 1 minus e in the power of minus x over theta. So probability that x is going to be less than b, it's going to be equal to the cumulative distribution function at this point b, and I just need to substitute the b to here. It's going to be 1 minus e in the power of minus b over theta, which is 11, right? And if I cancel out everything, it's going to be e in the power of minus b over 11, and it is known that this is equal to the 1 over t. So in order to evaluate this, I'm just going to take the ln, right? It's going to be ln of minus b over 11 is equal to e in the power of this, right? This is equal to the ln of 1 over t, or I can write this as a t in the power of minus 1. Okay, so if I cancel out everything, it's going to be equal to b over 11 is equal to the ln of t, or from here I can find that the b is equal to 11 multiplied as the ln of t. So second problem is, what is the expected life of 6-hour old component, probability that expectation of the x, given that x is more than 6. So we are going to use the memoryless property, right? So the exponential distribution having no memory, this is the 6 plus unconditional expectation. So this is going to be, so if the so we are given that the expected time for that the component works, and it is 11 hours. So if the component has already worked for 6 hours, what is the expected time of this component? So we are going to use the memoryless property. This is going to be equal simply 6 plus the expected of the x, right? So when it works 6 hours, everything starts from the beginning. So it just forgets everything what happened before. So this is going to be equal to the 6 plus 11, or simply 17. And the last problem is, find the probability that a 6-hour old component will survive another 5 hours. Basically, find the probability that x is more than 11, given that x is more than 6. So we are going to find the probability that x is more than 11, given that x is more than 6. Just using the memoryless property, this is going to be equal to the probability that x is more than 5, or simply this is going to be 1 minus f of 5, where this is going to be equal to the 1 minus e in the power of minus 5 over 11, or simply e in the power of minus 5 over 11. So problem number 6 is about a hypothesis test. A list of ages of the actress when they won the Oscar is given. Okay, so the list has, the sample has 82 items. We calculated the mean of the sample, and this is equal to the 35 and 9. And we also calculated the standard deviation is equal to the 11.1. So we are going to use the 1% significance level to test the claim that the mean age of the actress when they won the Oscar is 33 years old. Right? So the claim is the mean age of the actress when they won the Oscar is 33 years old. So the claim is mean is equal to the 33. So this is going to be equal to the null hypothesis. This is our claim. And the alternative hypothesis is equal to mu is not equal to the 33. So since the sample size is more than 30, we're going to use the Z distribution for the samples mean. So this is our first step. In the second step, we need to identify the test type and find the rejection regions, right? So since the sign of the alternative hypothesis is not equal, it means that we're going to have the T rejection regions on the boss of the TL. So the rejection region is going to be here and here, right? So since the level of significance is simply 1%, so the total amount of the areas here should be 1%. This is going to be 0.005, right? So 0.5%, and this here is the area is also 0.005. So we need to go to the table and find a value of the Z when the area is equal to the 0.05. Minus T.58. Minus T.58 corresponds to the value of the Z. T.58, it's here. Basically, probability that Z is less than minus T.58 is equal to the 0.005. Okay, so we found out the critical values. So in a third, we need to calculate the test statistic. So the test statistic for the mean is calculated. Z is equal to the x bar minus the mu divided to the standard deviation multiplied to the square root of n. This is going to be equal. So the test statistic in our case is 35.9 minus mean is 33 divided to standard deviation, which is 11.1 multiplied to the square root of 82. This is going to be equal to 2.9 divided to the 11.1 multiplied to the square root of 82. So this is going to be equal to the 2.36, and then to find the value of the 2.36, it's going to be here. Okay, so 2.36. That's here. It's not in the rejection region. It means that the null hypothesis is true, right? So we say that there's not enough evidence to reject the claim. There's not enough, so the null hypothesis is true. There is not enough evidence to reject the claim. And the last problem is on the confidence intervals. So from a poll in which respondents were asked if they felt that US nuclear weapons made from the feel safer, so N is equal to the 1005. So we asked like 1005 people whether they feel safer because of the US nuclear weapons, and 543 of them say yes. It means that the sample's proportion is going to be equal to the 543 divided to the 1005. This is going to be equal to the 543 divided to the 1005. It's 0.54, or simply 54%. So estimate the population proportion with the confidence level 80%. So we are going to estimate the population proportion by subtracting the error margin from the P and adding the error margin to the P. And we are going to calculate the error margin by multiplying the z to the pq divided to zn. So p hat and q hat. So this is going to be, so z, the critical point which corresponds to the 80% of level of confidence, is found in this way. So the level of confidence means that the area in the middle under the standard normal distribution curve is equal to the 0.8. It means that this area is equal to the 0.1 because total area should be 1, right? So we need to find the value of the z which corresponds to the 0.1 or 0.9 if we have the positive table. It's going to be equal to 0.9 is 1.28. 1.28 was the minus and 1.28 was the plus. So the critical point is going to be 1.28 multiplied to the p is equal to the 0.54. Q is 1 minus p, which is 0.46, divided to the n, which is 1005. So let's evaluate everything. It's going to be equal to 0.02. So that is why the confidence interval is going to be equal to the 0.52 and 0.56. So we are 80% confident that the population proportion who feel safer about the nuclear weapons is between 52% and 56%.